Thank you, Kelly. So in this demo, we will show you a vRouter running in the multi-cloud service provider network, providing cloud connectivity to customers. We will start with customer A, who is connected to the three cloud services, Azure, AWS, and Salesforce. We will review the vRouter configuration using the CLI. We will see how customer A is isolated in its own VRF, how it is connected to the customer network and the clouds using VLANs and BGP, and how QoS is used to ensure the customer's SLA. We will also demonstrate how the customer can be monitored using a time series database and a graphical analytics with InfluxDB and Grafana. Then we will add customer B, this time configured using Ansible and netconf to demonstrate automation. We will show how customer B can be monitored in its own dashboard. And finally, we will show a third generic dashboard for general monitoring of the vRouter. Let's switch to our demo. Let's start by reviewing the configuration of the vRouter for customer A using the CLI. Each customer is configured inside its own VRF. This maintains isolation between customers. We can see the VLAN interfaces used towards the cloud services on one side and the customer's network on the other side. This customer is connected to Salesforce, AWS, and Microsoft Azure. QoS is used to enforce the SLA subscribed by the customer. In this case, 1 gig of bandwidth is configured globally on the VRF. However, of course, more performance can be configured. As we showed in our customer Southern's use case, Southern exceeded its 5 gigabit per second throughput metric for BGP, firewalling, and IPsec VPNs when testing traffic from data center to AWS. Let's now review the routing configuration. A BGP peer is configured with each of the cloud services and with the internal customer network. Route maps and community lists are used to configure route redistribution so that link local addresses and routes belonging to a cloud service are not duplicated. We can now check the routing state in the VRF. We see the route in 1091 towards the internal customer network and the routes in 172.16 towards the three cloud services. Let's now simulate some traffic between the customer networks and the cloud. We start a traffic capture on the VM emulating the cloud service, and we launch a ping from the VM located on the customer's network on the other side of the vRouter. This will use the routes learned through BGP. While the traffic is running, we can review the configuration of the KPIs that are retrieved from the system. These include product information, such as license and version, system information, such as CPU or memory usage, networking statistics, and others. These KPIs are periodically exported to an InfluxDB time series database and will be displayed in a Grafana dashboard. In the dashboard for this customer, we see the RX and TX throughput of each interface. This includes instance throughput in a gauge and variation over time as a curve. On the top, we see the VLAN facing the customer network, and on the bottom, we see the three VLANs towards the cloud services. This is a simulated environment focused at showing functionality, so the throughput is quite low here. Let's now configure customer B on the vRouter, this time using Ansible and netconf. On the management VM, a simple Ansible playbook is configured to apply a netconf configuration described in an XML file. A quick review of the XML configuration shows us it is similar to customer A's, including a VRF, QoS, routing, and VLAN interfaces towards two cloud services and the customer's internal network, and of course KPIs. We execute the playbook and are now ready to review the configuration of the customer in VRF2. Using the CLI, we can see as before the BGP configuration, the VLAN interfaces, the QoS, and the KPIs. The BGP state includes the 1091 internal network towards the customer's LAN and the 172.16 networks towards the cloud services. As previously, we can capture traffic on a cloud VM and ping from a VM on the customer's network. In Grafana, the dashboard for customer B is very similar to the one for customer A, except we only have two interfaces towards the cloud services. As before, we see the RX and TX throughput of each interface, including instance throughput and variation over time. We have seen the two dashboards that the service provider will expose to each customer. To conclude, let's have a look at the general dashboard used by the service provider to check the status of the vRouter. We can easily see system uptime, vRouter status, memory and CPU usage, network interfaces with their throughputs, process and users information, disk usage, and IPv4 neighbors and routes configured in the system. It's all available in a single, easy-to-use dashboard, which is important as we allow service providers to manage over 100 customers per vRouter. So this concludes our demo. The demo platform was focused on demonstrating functionality. In a real use case, the 6-WIN vRouter for multi-cloud service providers scales from 1 gig to more than 100 gig of connectivity, can support more than 100 customers per vRouter, leverages an extensive feature set, including the VRF, BGP, and QoS features we have demonstrated, supports the NetConfig API for integration with automation tools such as Ansible and customers orchestration systems, and provides telemetry for advanced monitoring and analysis by streaming KPIs to a time series database, which can then be displayed in a graphical tool. In our demo, we used InfluxDB and Grafana, but others are possible. It's a very scalable, flexible solution and easy to use. This is why customers like Southern have been having tremendous success with our vRouter. Thank you for watching my demo. I will now turn it over to Q&A.